They basically made a radiation glory hole.
Can't say I've heard that one before. Today we're going to be looking at another one of Plainly Difficult's videos. Specifically, radiation on a crowded public bus. For those of you who don't know me, I'm Tyler Folse. I'm a nuclear engineer with a little over 10 years of experience in the commercial nuclear power industry. From engineering operations to emergency response. I don't claim to know everything there is nuclear, but I can certainly share some knowledge. Let's see.
I don't enjoy coach journeys. They give me really bad travel sickness. Something about bouncing around, old smelly seats, and the lack of proper toilet facilities really don't vibe with me. I would always prefer a train for a long distance journey, but maybe my travel sickness is from another reason. Well, today's story makes me think there is. In 2002, an intercity bus in Bolivia ended up being the cause of multiple people being exposed to radiation. Yes, you heard me correctly, a radiation bus. But it's not for what you think.
Yeah.
The bus wasn't nuclear powered, it was running on good old diesel.
Now, a nuclear powered bus is an interesting idea. You'd have to make it a microreactor, which would be challenging because placing adequate radiation shielding, heat shielding, and all the redundant safety features you would need would be challenging to fit into a bus. About the smallest we've gotten is in a submarine, which is a lot bigger than a bus. But you could potentially make just a really big bus. You might be better off making a train. If you were to do it, you would definitely want to use something small and dense, such as a molten salt reactor design, but it would still be way bigger than a normal bus. But if you did, it would be one with no greenhouse gas emissions. You wouldn't need to refuel it very often, and it could pave the way for nuclear-powered aircraft, trains, even cars, though miniaturization is a ridiculous challenge, and it would also be extremely expensive. So I don't see this happening anytime soon. Plus, you'd have to train the bus driver to be a licensed reactor operator. Be a very expensive, high-paying job to be a bus driver, in this case.
It was more its cargo that was the concern.
Yeah.
Stay tuned to find out more. Today, we're going to have a short dive into the 2002 Cochabamba radiological incident.
Okay.
My name is John, and of course, you're watching Plainly Difficult. Background. So for this section of our video today, I'm going to talk about this organisation, IBNORCA. It is a non-profit that was formed in Bolivia in 1992.
Yeah.
It is responsible for setting national technical standards. It replaced a government organisation that undertook similar roles. The organisation also issues quality control certificates and
an NGO replacing a government organization for things like quality and safety. I can understand supplementing one or creating even higher standards, such as in the US, the regulators, the Nuclear Regulatory Commission, but after the 3 Mile Island accident, there was the Institute of Nuclear Power Operations, which is technically an NGO consulting group, but for all intents and purposes, it's another regulator with even higher standards than the federal government. But I've never heard of it being outright replaced or outsourced or privatized regulation.
Operates accredited training for various industries. The company has around 40 employees, well, at least in 2002, where our video is concerned. It has a few subsidiaries. One for today is rather important, and that is the National Centre for Welding. This part of the company offered a service for non-destructive weld testing. This was done with a single 192 iridium special form sealed source housed in a Model 660 remote exposure container made by AEA Technology QSA Inc., which is a US-based company. Due to there only being one unit available for the company, and because testing is done both in the field around Bolivia and at their shielded radiology facility on Avenue Camacho in La Paz, the equipment got a lot of usage and also a lot of transportation. Now, because IB Norca used radiography equipment, they fell under the regulations of the Bolivian Institute of Nuclear Science and Technology.
Okay.
And in 1990,
So radiography is used quite a bit in nuclear power plants. What it involves is you use X-rays to look for defects in your welds, junctions, really anywhere, but the more likely scenario is a flaw will show up in a weld or any sort of connection to a vessel or a pipe or whatever it is you're inspecting. And as you can imagine, nuclear power plants have extremely high requirements for their welds and their fittings. So this testing is done either after a big maintenance window, say during an outage where there's a lot of welds were done, or periodically to essentially manage the aging of important plant components and help decide when it's going to be time to replace them, or say, no, you're good to essentially run this component for another 10, 20 years or what have you. It can also be used for containment integrity analysis. You can look at the concrete that makes up the containment building, and you're mainly looking for leaks and flaws. And this is also done even in the non-nuclear part of the plant, the turbine building, the heat exchangers, pipes, basically a form of a leak check. And considering nuclear power plants have radiation protection experts that live at the plant rather than, say, a non-nuclear plant where you essentially need to send radiation protection technicians over there with your radiography because, again, high energy radiation is involved, X-rays. So that's one benefit of nuclear power plants is you already have a bunch of experts on site anyway, at least as far as dose management is concerned. But he mentioned iridium. Iridium-192 is a mixed emitter, does both betas and gammas. In the case of radiography, you would be using gammas. And the reason for gammas over X-rays is it's higher energy and it penetrates a lot deeper. So if you want to image thick, dense material, sometimes you need gammas. So you would use something like Iridium-192 or Cobalt-60.
1997, new rules came into place, where all companies needed to be licensed and properly regulated in line with international standards. IB Norca didn't apply for their license until 2001. We'll come back to this in a bit later on in the video. Anywho's, the single 192 Iridium device worked like this. They had three main parts: the source container, a guide tube, and a 20-meter long drive cable with a crank at the end. The container had from outside to inside an outer shell, then polyethylene foam around a depleted uranium shield around a source tube, which is in an S shape, which had plugs in.
Depleted uranium, so uranium that has essentially used up all the fuel that you're going to use for it in a nuclear power plant. It's very dense, and so it would be effective at shielding from gamma radiation.
Each end. Inside there was a source pellet, and at one end of this there was a 15-centimeter cable attached to it, and this is called the pigtail. When in use, the pigtail is attached to a 20-meter long drive cable, which is then in turn attached to a crank. The guide tube can be extended by adding pieces, the end of which is known as the snout. This is placed where the radiography exposure is meant to take place. So before an exposure, and while still safely wound inside the container, the snout is placed at the weld that needs to be tested. A piece of photographic film is placed behind the weld. The crank is operated until the source grain is wound out to the end of the snout. A pre-calculated exposure time is waited whilst gamma radiation is given off by the Iridium-192 source, which the gamma rays pass through the material being tested. As they pass through, some are absorbed more or less depending on the thickness of the material. The more that is absorbed means the area is thicker. Thus, if less is detected, then the material is thinner, and in the weld, this hints towards a void, crack, or other defect.
This is just like getting your X-ray done, because that's what it detects in your body to see if your bones are broken, if there's essentially defects in your bones due to injury. This is just higher energy.
The photographic film captures this, and after processing, will show the darker spots and lighter spots. And darker means more rays have passed through the material and is thus thinner. I think I kind of explained that okay, but sorry if I didn't.
Not a bad explanation at all. That was fine.
So in a machine like this, Making sure your radioactive source is safely housed is important, wouldn't you say? Yes,
Oh, yeah.
obviously. However, keep that also in mind for later on.
There would be, when the device is in use or even set up for transport, there's radiological briefing, just like there is with anything else that you do when you're handling radioactive material, or not even handling it, but it's in the vicinity and people could potentially be exposed to it. Areas where radiography is occurring are routinely blocked off just to minimize overall dose as much as you can. It's another reason why radiography is typically done during an outage. Another reason, as I'm sure you can imagine, is on the reactor components themselves. If you're doing radiography there, obviously the reactor being online would cause interference due to the high neutron field.
IB Norca is employed across the country to undertake non-destructive testing, which requires transporting of their equipment. How would you say that this is done? Private car, van, plane, train? Well, how about on a public bus service?
Oh my. So I'm not an expert on Bolivia Department of Transportation, but within the US, there's very strict standards for transporting radioactive material or even hazardous material in general. You try to keep it away from public areas, both in terms of the type of vehicle involved, say the type of truck. It would be marked accordingly. You saw earlier he had a radiation hazmat label on there, and that one looks similar to ones that you would see in the US. There's also signs that look like this for the paths that you can't take your hazardous material through. Those are typically through city centers, so you basically have to take the long way. And radiation sources would be included on that list.
That is exactly the way the company would transport its equipment, by booking it on the Bolivian equivalent of a Greyhound bus as cargo.
That's crazy. So if you were to attempt to do this with, say, the standards that I'm used to, everyone involved in that vehicle would need a radiological briefing and would also have to be qualified as radiation workers. Something tells me that's not what happened.
This would later be cited as one of the reasons for the company's operations license refusal, which also included staff not having undertaken the appropriate training, out-of-date dose meters, and improper paperwork supplied with their application. Also, the whole transport issue required them to have a vehicle with correct signage and proper controls for a radiological incident. Things that most public transport buses don't generally have.
No.
But luckily for them, their 2001 kickback wouldn't affect their abilities to work, as it was during a transitional period where the companies were given some time to improve.
Wow.
The radiological accident. It is 9:30.
Yeah, there would be an all stop. You're not getting any time to... Just no.
30 on the Saturday, 13th of April 2002, and a coach is pulling into the airport at Cochabamba. Aboard the cargo area is IB Norca's Type 660 remote exposure container, housing its 0.67 terabecules of 192 iridium source.
So what that means is just under 1 trillion decays per second, or about 30 million times more radioactive than a source in a smoke detector. And this is gamma. So yeah, not surprised that people got sick on this bus if something like this was not properly contained or controlled.
It had been transported to Cochabamba from its last job in Uro. In Cochabamba, the radiography machine is to be used to check the welds on some 2-inch gas pipelines, which are being installed near the airport. After its journey on the bus, the
2 inches could probably get away with using X-ray rather than gamma, but...
radiographer from IB Norca checked the container with a dosimeter. The readings made him confident that the source was correctly seated inside the source container.
Okay.
This would be the only dose rate reading that this person would take for their session today. At between 10 and 11:30 in the morning, the radiographer made 10 exposures of the pipeline. Now, as required by the company's rules, he should have checked his dosimeter to make sure the source was back in the container.
Oh, absolutely.
But he didn't.
That's part of the principle of leaving stuff as you found it, or leaving stuff better than you found it, in terms of cleaning up and verifying that after you're done with your tools, they've been properly put away.
At the end of the session, the radiographer started to pack up the equipment, but he found a little bit of an issue. He could not turn the mechanical interlock required to remove the drive cable and crank. This would be activated when the source was not fully retracted. However, the radiographer had wound the cable back enough, but the source and its pigtail had actually become disconnected and was stuck somewhere within the source tube. The radiographer didn't know this. If he used his dosimeter, he would have. But it would turn out that he didn't. Instead, he assumed the source was inside.
So this is weird because most dosimeters, while you're working with radioactive material, are on. You would have something in the vicinity. Because, okay, what if something was wrong? Like you had an issue in some of the pipes. You have like a leak or something. Generally, you need some sort of area dosimeter is utilized. Now, I'm coming from use to nuclear power plants. Depending on the procedure with the airport weld job, they might not require one, but to me it just seems weird.
The container, and it was likely that some dirt had maybe got into the interlock.
Yeah.
He continued to try and free the cable until around 12 p.m, after which he called the IB Norca office in La Paz and explained that he thought what the issue was with the source container.
Okay.
So the office told the radiographer to pack up the device and ship it via coach back to La Paz. But he had a problem. It wouldn't all fit in the regular transport carry case.
Oh no.
Instead, he did this. What is going on here? Well,
dude. So something marked with radiation and connection going into cardboard box. Or you gotta send it Amazon Prime. Well, it's 2002, but still.
He placed the source container at an angle in the carry case, and then placed the source tube, crank and drive cable in a cardboard box, all held together with a good old bit of tape.
No.
This very safe and well-confined arrangement was then taken to the bus station for transport.
I mean, do I even need to say what else is wrong with that? I mean, come on.
Aboard the 1600 service from Cochabamba to La Paz. The journey would be roughly 8 hours, and upon departure, It had 33 people aboard. By its destination, it was at full capacity.
Another thing is, I've never heard of any sort of, like, if let's just say it's welding equipment or whatever, putting it in a public transport. I mean, usually it'd be, that's just so weird. Like, you'd think he would, like, throw it in the back of a pickup truck or something like that. But like, no, I'm going to put it in a public bus. At least if it was in a pickup, he would be the only person affected.
55 people. This was due to the bus making stops along the way. The radiography machine was sitting the whole time under the passengers' feet in the cargo hold.
People getting unmonitored dose and gammas, improper shielding in your cardboard box. Oh yeah, to attenuate most gammas, you're going to need a few inches of lead. So the paneling in this bus is not going to do anything for you in terms of stopping gamma radiation.
Arriving in La Paz at around midnight, the bus's passengers made off onto their connecting journeys. The cargo was left aboard the bus overnight for unloading in the morning. 2 members of staff arrived at 10 a.m. to collect the package, but due to another staff member's name being on the address label, they would have to return at 2 p.m. with this member of staff to get the package released to them. Once claimed, the package was placed in the boot of a taxi for a 10-minute journey to the company's offices.
Nice.
Don't forget that each time the package was...
I wonder how much the surcharge is for a radioactive source. I know a lot of cab companies have surcharges for like extra baggage. Yeah. Wow.
...was moved, no one thought to put a dosimeter over it to check it.
They leave it open too?
The free workers manhandled the radiography.
I mean, it's gamma, so it doesn't really make a difference, other than the fact that it could fall out. Just leave it open.
Machine into the shielded room at the office. During the movement, no one was wearing any personal dosimeters. It was only after the radiography machine...
That's the other thing. You would be wearing personal dosimeters in addition to having an area monitor, is what I'm used to within a plant. I can understand no area monitor at an airport, maybe. You got to have dosimeters. I mean, if, X-ray technicians at a hospital wear dosimeters way, way less than a radiographer certainly needs to.
Was inside the shielded room, but a dosimeter was finally used to check the radiation of the machine. The dosimeter started going crazy. It was telling him that the source was not in a safe position. Not only that, but the rates were too high for the meter, not allowing the staff to figure out exactly where the source was, either in the container.
Apparently the source is everywhere, judging by that logic. They'd break the source.
Or in the guide tube. After checking it over, the staff came to the conclusion that the source must be in the guide tube.
Probably had to get a bigger
In order
dosimeter.
to figure this out, they used a cable hole in the containment's wall to push the tip of the source guide tube through to see if the radiation reduced or not, to find the exact location of the source.
So one thing, so they mentioned the activity as in just under 1 trillion becquerels. That doesn't tell you everything, so that's just disintegrations per second. It doesn't tell you anything about the dose to the human body. Like, is that a lot or not? Well, in the case of it being a strong gamma source, yes, and why it needs to be properly sealed. But by itself, that doesn't tell you what its effect on the human body is. That's just measuring raw radioactivity. You need something like sieverts to measure essentially the dose equivalent to a human, which is what these dosimeters that they should have been utilizing should have been looking out for.
They basically made a radiation glory hole. After discovering
Can't say I've heard that one before.
where the source was, it was reattached using tongs and wound back into the container. The event was actually now over, but
I still can't with radiation glory hole. What?
the IB Norca director wasn't informed until the next day, who then also didn't inform the government body in charge of radiography, IB10, via writing until the 17th of April, 4 days after the initial issue at Cochabamba.
Oh my.
In the meantime, multiple people had been unknowingly exposed and thus not properly treated.
Everyone on that bus.
Aftermath.
And probably several people at the bus passed by, but I mean, most other drivers would generally pass a bus, so it's probably not as much. But basically anything this bus went near has an unmonitored dose, even if those weren't enough to get people sick for like passing cars. That's still some unmonitored dose, essentially turning this into an orphan source. All kinds of regulatory no-nos have occurred here.
Dose rates for the 4 staff members were made, estimating the maximum to be 0.72 gray, which would end up with
0.72 gray. So gray is a unit of absorbed dose, so think energy per unit mass, joules per kilogram. This is gamma, so it's essentially 1-to-1, so 0.72 sieverts. That's enough to get radiation sickness. By itself, not likely to cause permanent damage. I said not likely to, that doesn't mean it's impossible, but usually that's at higher doses on the order of 4 sieverts, where a couple of sieverts, it can get really bad. 4, you're looking at what's known as an LD 50-60, that's 50% of the population dead within 60 days.
With recommendations of blood testing. And after a number of tests, luckily, nothing concerning showed up.
No.
But it wouldn't be until July that the bus passengers' estimated doses would be attempted. Don't forget, they were sitting above the exposed source for up to 8 hours. This was put at the highest estimated dose at 2.5 gray, way
That's nasty. That's, at a minimum, quite a severe sickness.
higher than the staff members. Finding these people proved to be near impossible, even though extensive newspaper and TV advertisements were placed. For reference, a whole body dose of anything above 5 gray can be deadly.
Yeah, and that's right. And now keep in mind, that's gray for gamma source when we're talking 1-to-1 dose. If you're getting neutron dose that's on the order of 5 gray, you're not going to make it. Because the multiplier for slow neutrons is ×5, and for fast neutrons can be up to ×20. Yeah, obviously not in the case of this accident, but I just want to show that grays are not always the same as sieverts, and 10 sieverts, death is all but guaranteed.
The event resulted in the IAEA being called in. They undertook experiments with a similar bus to work out the potential doses the bus passengers would have received, and the results were far more reassuring, with a maximum high of 1.2 gray at the feet of the seats over the cargo area. And although higher than recommended for the public,
Love the "you might be glowing." The wheels on the bus glow round and round. Should probably sing that version to my son.
A dose as much as this is fairly low in the grand scheme of things. It would turn out that IB Norca was rather lucky. The company would be hit with some legal issues, and this included, as stated by the IAEA, a maximum fine of 10 minimum standard monthly salaries. This was approximately $500. Seizure and decommissioning of the radiography source and container. The temporary suspension of all radiography work by IB Norca, the obligation to identify and locate people involved in the accident, and finally, the re-export of the radioactive source to the supply.
Depending on how they enforce the fourth one, that could actually be the most damaging. If it's, well, just identify and locate, maybe not necessarily them being involved in all of the damages. All in all, compared to what this could have been, this could be, these consequences weren't really that severe.
Not the worst penalty, I know, especially when the outcome could have been on Goiânia levels, if the source had been higher in levels of radiation, or if the source was a different one, for example cobalt-60, which does have a much longer half-life. Regardless,
well, really you're looking at just overall activity and energy level. Half-life by itself doesn't tell you the full story, but now the half-life would be nasty in terms of if the source got lost because of how much it would do over time. But in this case, where it was promptly discovered, half-life isn't that much of a factor.
It was a very close call. So that's my video on the Cochabamba disaster.
He has a scale?
Going to be a 1 on the scale.
Sure, yeah, no one...
And this is what I've got for my root cause analysis card. Do you agree? Let me know.
Okay, root company blanks, but... Oh man, that's hilarious. So, this accident has been studied. I mean, mentioned IAEA. The nuclear industry looks at accident reports all the time. And some improvements that I'm aware of from this incident are improved documentation and tracking systems, such as tags on your sources, just to prevent them from being lost in the case where this one easily could have been. Enhanced regulatory frameworks. There's whole radiation protection procedures from cradle to grave management of radioactive materials, and I mean grave as in when the thing has fully decayed away. So that includes the management of long-term nuclear waste. But for something like this, just don't put it on a bus. Keep it isolated. Add radiation monitors in addition to personal dosimeters that are required. All it would have taken was one of those, and people would have realized something was wrong, and the thing never would have gotten put on the bus. Again, could have easily been prevented. Thanks so much for the recommendation, and thanks so much for watching. I'll see you next time.